Hello, Science Alliance. Hello, my IGCSEers. We're right in the middle of our IGCSE physics module. I can't believe that. So we've pretty much done energy, and we've got all of like solids, liquids, and gases to go. I've put this one in the middle because technically it's part of energy, but it fits in very well with solids, liquids, and gases. We are learning about conduction and convection today, which is how heat travels through solids and liquids and gases. I am just checking you know, I'm sure you know this, don't you? You know that a place with no particles in it at all is called a vacuum? You know that. And you know that space is a vacuum. So there are no particles in space. We did this, if you've seen our waves lessons. We've talked about how in space no one can hear you scream because there's no particles to bump into each other to carry a sound wave, right? So yeah. A vacuum is a place where there are no particles. That might help you to answer a question a little bit later on. First of all, with apologies to people who've already seen this in some of my all ages lessons, I'm not assuming that everyone is watching all my lessons. So this is, I think, the first time we've looked at this in IGCSE. Which of these diagrams, please, that I have on the board now, best represents how the particles are arranged in a solid and a liquid and a gas? I've put, can you label them if you've printed the worksheet off my Facebook group? One of them is this there to trick you. It's not a good model for any of them. So solids and liquids and gases, right? They're all made of particles. They might be atoms, or they might be atoms joined together to make molecules. We'll just call them particles, and we'll think of them as little balls. How are they arranged in a solid and liquid and a gas? We've got a box where there's sort of lots of balls, and there's gaps between the balls, and some of the balls are touching and some of them not. We've got a box where all the balls are just very neatly arranged in very rigid rows. We've got a box that's only got 2 balls in it, and we've got a box that has got more balls in it, but they're not touching each other. You've got 5 seconds while I test my pens. My poor, sad, dying pens. There we go. Okay, well, I was thinking you would probably get the solid one. Yes, particles in a solid are arranged, can be thought of as arranged in these extremely rigid rows, yes. And I thought you might get the gas one. So gas particles are very far apart. Gas particles are not bonded together at all. In solids, they're all bonded together very strongly, and they are still moving. We'll talk about what happens if they stop moving in later modules, but the particles in a solid, like, you know, your skin or the metal spoon or this whiteboard or whatever, they're all vibrating ever so slightly, but just on the spot in a fixed place. Gas particles, particles of gas, are free. They're not bonded to anything. They're just all moving around all over the place, and they're pretty fast spread out. In a liquid, this is the one that trips people up at GCSE level. In a liquid, they're actually still very close together and even touching each other. People often imagine that it's just a bit more spread out, or it's like a gas that's a bit closer together, but that last one isn't really anything. I've put, maybe it's quite a dense gas. It's a gas where the particles are close together. But yeah, in a liquid, the particles are, they're still touching each other. They're bonded, but the bonds keep breaking and then reforming again. So it's kind of like a ball pool. Right, we have done this activity, I think, already in our electricity lessons, but if you've got a metal spoon and a wooden spoon, it's just such a good thing to do. Pick them both up. What temperature are they? How cold are they? How warm are they? Is there a difference? There is a difference. The metal spoon feels colder. Why? Why does the metal spoon feel colder? Can you remember if you came to my electricity lessons? The metal spoon definitely feels colder. Now, I'm assuming that, like me, your metal spoon and your wooden spoon have been in the same room for like a really long time. You haven't kept the metal spoon in the fridge or anything, so that surely there's no reason why they wouldn't be the same temperature. They're in the same temperature room, but the metal spoon feels colder. Why? Well, what it is how it works is, right, your body is warmer than the spoon. You okay with this? You're a mammal. Your body is warm. So your body, I guess, is made out of is a solid. So the particles are quite closely arranged. Let's say that these are the particles in your body. Let's put some little like movie bits. These pens. Just spent my entire morning throwing pens across the room. So they're vibrating a lot, right? The warmer particles are, the more they are vibrating. Again, we'll look at more of this later. The wooden spoon, the metal spoon, those particles are colder. I'll just draw cold to be blue. I know, we'll get to astronomy and we'll realise that that's not right. But anyway, what's happening is, it's kind of like dominoes. the particles in your hand are vibrating a lot, and they are knocking into the metal particles of the spoon, and the metal particles of the spoon are knocking into each other, and heat energy is getting passed from your hot body to the cold spoon, right? That's why you're feeling that the spoon is colder, because the spoon is literally shifting heat energy away from your body. I know. The wooden spoon doesn't do that as much because its particles are just arranged in a different way. We'll talk about that more in a second. That's what I would tell you if we weren't doing IGCSE. Because we're doing IGCSE, we have to go like a little bit deeper. Do you remember when we learned about electricity? I told you that the particles inside metals were arranged like a lattice. So they've got the protons, the central part of the atom, if you like, that's frozen in one place vibrating. But actually all the electrons that usually whiz around the protons, they're all free. These little blue particles that I've drawn here, they're all just free to move around, like wherever they like. They are free electrons. So that's why metals are really good conductors of electricity, because electrons moving is just what electricity is. I've put latticey because, I don't know, someone thought it looked like the top of a pie, so they've called it this lattice structure. But the fact that these electrons are free is also why heat energy travels really easily through metals. So the free electrons are, again, like they're gaining energy from your hand, and they're whizzing away with it, and I guess more electrons are taking their place. So in things like plastics, the particles are kind of all wound up like spaghetti, and this doesn't happen. So something that is a good conductor is something that allows heat energy to flow through it, right? And metals are very good conductors. Do you think that liquids or gases are good conductors? Could be one, could be both, could be neither. What do you reckon? Here we go. You've got your diagram back of the liquid and the solid and the gas. Do you reckon liquids or gases are good conductors? 3, 2, 1. No, they are not. It's like just in your specification for both of them that you need to know that they're just not, because there's gaps in between them. Right. I think you're ready for my sheet. So actually that's one of the reasons, I'm talking very quickly, I'm excited. One of the reasons wood is not a good conductor is because it's got lots of air trapped in it. So if we were talking about air, obviously it's not a good conductor because there's just hardly anything here. Like occasionally an air particle will come and bump into your warm hand and then travel away again, but heat isn't passing through it in the same way. I'm going to stop talking. You do my sheets. It's not really designed for you to get perfectly right answers, isn't this? It's a brain exercise before we move on. So can you please tell me, are these scenarios conduction? You could write, if you've got the sheet, mostly, a bit, or no. What do you think? Is it conduction? So is the sun heating the surface of a swimming pool? Is that conduction in action? Is that particles passing along heat by kind of bumping into each other? Soup heating on a stove, is that conduction? Mostly, a bit, or no? A radiator heating a room, is that conduction? An ice cube making your hand cold, what do you reckon? The handle of a toasting fork getting hot, and if you imagine this fire over here, I've got some Lego Story Time fire, here we go. If you imagine this fire all the way over here, that marshmallow getting toasted, is that conduction? Mostly, a bit, or no? How are you doing? You might be finding this really difficult. Like I say, that's totally fine. It's really just to get you thinking about it, and then we'll go through it. Okay, should we go through it? So I was desperately telling you what a vacuum was earlier. The sun heating the surface of a swimming pool. There's just not any solids involved at all, are there? So you've got the sun travelling through space, which is a vacuum, through air, which is a gas, and then heating a liquid. So that is definitely not conduction. We'll look at next week how heat is travelling, radiation next week. Soup heating on a stove, yeah, that is very much conduction. So the stove is hot, and the hot stove heats up the particles of metal that are next to it in the pan, and then those particles bump into each other, and the free electrons shift the heat through the pan until it gets to the soup, and then the soup gets hot. So yeah, that would be a radiator heat in a room. Yeah, I've put a bit. I mean, it sort of depends which bit you're talking about, doesn't it? So while you were thinking, I was drawing this magnificent diagram. If you're looking at like a close-up of the radiator and you've got water here, I suppose I should have drawn the water as particles as well, really. If you've got water particles here, which are hot, then they would bump into the metal particles of the radiator. This is like inside the radiator. And then those metal particles would vibrate and knock into these metal particles and knock into these vibrate particles until you got to the outside of the radiator. So yeah, the metal that the radiator is made of, how heat is travelling from the inside of the radiator to the outside of the radiator is conduction, but once it actually gets to the air, there's no conduction happening here, it's just air particles sort of bumping into each other. An ice cube making your hand chilly? Yeah, that's just a more extreme version of the metal spoon. Yes, there's a bigger temperature difference between the ice cube and your hand, so heat would shift more quickly, but yeah, that is conduction. The handle of a toasting fork getting hot, yeah, that's conduction, isn't it? Again, it's just like the spoon, these metal particles bumping into each other, free electrons shifting the heat. But the fire toasting, no, that's not, because that's heat travelling through the air from the fire to the marshmallow. Right, let's set up our next activity. We will start setting up so that was all conduction. Conduction is, yeah, basically how heat travels through solids. We're going to start looking at conduction, which is how heat travels through liquids and gases. So I'll set it up, but while we're setting it up, I'll tell you a little bit about insulators. So if you've got your 4 spice jars, you need to fill 2 of them with very hot water and dye it red, and fill 2 of them with very cold water and dye it blue. If you've only got 2 spice jars, just do 1 hot and 1 cold. I know loads of you have done this before with me, because we've done it in a couple of shows. In fact, we did a Lego Storytime show about convection a few years ago, but where we looked at like how, well anyway, I'll tell you in a sec. But we haven't done it yet in the IGCSE lessons. So I'm very excited that I get to do it again, because some of you will only be watching these lessons, and you deserve to see the awesome convection spice jar demonstration. Okay, so I've filled 2 jars with hot water, and I'm going to put some red food colouring in, and then I'll fill 2 with cold water, and I'll put some blue food colouring in. So let's just have a little chat while I'm setting up about things that are really bad conductors. If something is a very poor conductor, if something doesn't let heat travel through it, like gases, or liquids to a lesser degree, or wood, then it's called an insulator. I better write that down like a proper physics teacher. Insulation. So insulators are not good conductors. Not good conductors. They don't allow heat to pass through them. This has many uses which you need to know about for life, but also to get marks on the IGCSE. So here, while I'm just putting food colouring into things. So that's my 2 hot ones, I'll make those red. That's my 2 cold ones, I'll make those blue. Have you heard of a vacuum flask? You know how that works? Vacuum flasks, they've got water on the inside, and then they've got a layer, which is a vacuum. Yeah, right, there's no particles in it. They've sucked, well, there's some, but they've sucked most of the air out. So if this is very hot liquid and you want it to stay warm, then the hot liquid the heat can't conduct through the walls of the flask because of the vacuum there, right? So no particles to bump into each other. So that's one way that a vacuum flask works. Also the case on the outside, that would be made of some sort of insulating material, like maybe plastic, like I say, because the particles in plastic are sort of wound up like spaghetti, so they don't conduct heat very well. There we go. I'm getting there. 2 hots, now I do need to dye my 2 colds. Other examples? Oh yeah, here's some homework for all of us. Have you ever heard of baked Alaska? You can tell it's quite an old-fashioned dessert because of the photo. It looks like it's from, I don't know, the 70s or the 90s. But yeah, baked Alaska is hot meringue on the outside, but on the inside it's ice cream. So you get a biscuit, you put a load of ice cream on top of it. So I'm just stirring in food colouring. You get a biscuit, you put ice cream on top of it, and then you cover it in meringue and you bake it in the oven. And the ice cream doesn't melt. So it's amazing. You get hot meringue on the outside and ice cream on the inside. How much do I want to do that? How does that work? Come on, you should know this by now. If you know about meringue, now you know a bit about insulators. How is the ice cream getting insulated from the heat of the oven? It's quite a few reasons, but one of the reasons is the air. When you whip up a meringue, you trap air, don't you? So that means that it's an insulator, so it can't conduct heat through the meringue. Please, come on! I'm gonna try. I really want to have made this for next week. You could, if you're vegan, you could try it. I might try it with like that chickpea water and see if it works. We could be on something here, guys. Another example, it has been bonfire night quite recently, if you're watching live, so you might have toasted a marshmallow. You'll have noticed that the outside of the marshmallow gets crispy really quickly, but the inside the marshmallow is still pretty cold. That's because marshmallow's got a lot of air in it, yeah? So again, insulating the inside, very annoying. Here's something that you're more likely to see at IGCSE. Your double glazing windows have got a layer of air, or ideally even not very much air on the inside. So it's glass and glass, but with air in the middle, and maybe some insulation at the bottom, so that heat can't conduct through the glass to the outside. It gets stopped. And finally, here's someone sort of slightly self-consciously having their picture taken with some loft insulation. That's basically sort of wool. Sorry, I just realised I've forgotten my cardboard. Just cutting the lid off the side of some Weetabix. Yeah, loft insulation is basically just wool, and wool is an insulator, again, because it's just got lots of air trapped in it. Okay. So now you know about insulators, let's do our convection activity. I'm not going to tell you what convection is yet. Some of you might know anyway. What you've got to do is, first of all, you've got to move your laptop really far away from where all the little spice jars of liquid are. And then this went wrong for the first time ever on Facebook yesterday. Right, if you've only got 2 spice jars, put hot on top of cold. If you've only got 2 spice jars, put hot on top of cold. Don't do what I'm about to do now. I'm going to start by putting the cold jar on top of the hot jar. How I'm going to do that is, you just get a little square of cardboard, put it on top of the jar, push it, keep pushing it, turn it upside down, and because of air pressure, which we'll learn about later, it stays on. And then get it on top of the jar and pull away. I'll show you. I think this jug of water is just the right size, actually. Yeah, that'll do. You see that? So, yeah, a little piece of cardboard on top of the cold spice jar. Turn it upside down. If you've only got 2 spice jars, don't do this yet. Take it away, but don't be a hero. That's not the activity. And then, what do you think we're going to see? What are we going to see when I remove this cardboard and let the 2 liquids flow into each other? You ready? Ooh, they're mixing. Is that what you expected? Close up. Oh, I love this one. Here we go. So as you would maybe expect, we've got some purple at the top. We've still got some red at the bottom, actually. But yeah, well, spinning is probably a bit dangerous, isn't it? There we go. So you can see that the 2 colours are mixing together. All right, let's try that again then. This time, whoops, we'll do red onto blue. This is where yesterday, for the first time ever, I just ended up with massive spillage. That's why I say to do it on top of a baking tray. Didn't mention that, did I? Yeah, do all this on top of a baking tray. So now I'm going to put the hot on top of the cold. What are you expecting to see? Oh, it's hot. Oh, sorry, I should have said be careful if you're using actually boiling water. All right, remove the cardboard as quickly as I can. Oh, Look at that. Man, I love this activity. Oh, I've got to spin it around now so I can show you that way. Is that what you're expecting? I know some of you have seen this before. If this is the first time that you're seeing this, I'm so happy that I get to share this with you. Look, when the hot's on top, they don't mix together. You've got this little purple band from when I took the card away. They're not mixing. And if you're doing this at home, just keep it there for as long as you can. Honestly, days can go by and the two will not mix very much. Absolutely brilliant. What has this got to do with conduction? Well, it's very important for learning about convection, how heat travels through liquids and gases, that you know that hot things, warmer things rise, right? If you've been to my all ages weather lessons, we've been talking about this. So the reason that they rise, well, let's do a radiator example because I've got a radiator down here. So there's obviously lots of air in my room. My radiator is hot at the moment. So the particles of air above the radiator are hottest. Again, I'm going to show this with some very poorly drawn red circles. And the air up here is colder, right? What happens when air gets warm is the particles get more energy and they spread out. I will show this by deleting some of the worstly drawn circles. Yeah, particles that have got more energy, they spread out. In fact, we'll do a whole lesson on it later. So these warm particles, they spread out and they have become less dense, right? Again, we're doing density later. Density means how close together the particles are. This air has become less dense because the particles have spread out. And things that are less dense rise up. So this is a lot if you've never heard this before. Stuff gets warm, the particles spread away from each other, so that air is less dense, we say, and less dense air rises. So that's what's happened with this activity here, is that the warm water is less dense than the cold water. So this is the natural way of things, that the less dense thing is sitting on top of the more dense thing. These water particles are slightly closer together. With this one, we had a more dense thing sitting on top of a less dense thing, so the more dense thing has sunk to the bottom, and the warm water had to go somewhere, the cold water had to go somewhere, so it's been what we call displaced and moved out of the way. Here we go. So yeah, the warm water, I can't be bothered to draw this anymore, but the warm air, because it's less dense, it rises up and it kind of pushes the cold water out of the way, the cold air out of the way in this case. So the cold air, and obviously it's denser, so it sinks. But what happens to the cold air when it sinks and gets to the bottom near the radiator? Well, it obviously warms up. So the cold air warms up, so its particles gain energy. So the particles spread out, so it's less dense, so it rises. So it gets to here, where the warm air that was there was cooled down and pushed out of the way. This is called a convection current. Convection current. We did about this in our all ages weather lesson, so I didn't use the word convection because I didn't want to scare them. Current. There. And I'm going to give you a little sheet about it now. Bring my laptop back into play because the food colouring has not spilled everywhere. Here we go. So, question number 1. We've got a kitten here and it's cold. Can you put the stages in the correct order to heat up this little kitten before her eyes get frostbite? This is quite hard, this, I think. Yeah, give me this. Put all these stages in order to describe how a convection current works. A, air particles gain energy. B, the radiator heats the air. D, then is heated by the radiator. F, so spreads out. C, cold air is pushed out of the way. H, and rise. E, and the cycle continues. G, and sinks. Put those in order, please. I kept trying to do it and then realising I'd missed one out and having to stick it in a different place. Question number 2, because I did write this, I just wrote it a couple of years ago. Can you add more stages to question 1 and include the words, well, you don't have to actually say more dense and less dense, but if you could use words, if you could talk about density, that would be good. So add some ideas about density to question 1. Question 3, you just got a picture here of somebody tossing some stuff in a pan by an open window, and there are clouds and fields outside, and there's pans on the shelf, and there's some salad in a bowl, and there's another hob here which has a pan of something on it, maybe soup. How many examples of convection can you see? Name and explain. And if you've got through all that, I need you to explain why the little freezers inside fridges are always at the top. If you've ever been in, I don't know, like a band practice room or something where there's a little fridge, then if there's a little freezer, it'll be at the top. Why is that? If you're on to question 4, can you answer it as if you were answering an IGCSE question? So on Facebook yesterday, a couple of people were saying, because cold air sinks, which is very good, it'd probably get you a mark, but can you be as full as possible in your description? Okay, should we go through it? These stages then. So the radiator heats up the air particles gain energy, so they spread out, so they rise up. And then cold air gets pushed out of the way because the warm air has risen up to where the cold air was, and that sinks. And then that cold air gets heated by the radiator, and the cycle continues. All right, so I said if you could talk about density. Oh, I've made a mistake actually, I just remembered. This is not quite right. Why is this not right? In fact, that's a very good question for you. The radiator heats the air particles gain energy, so spread out, becoming less dense. That's actually wrong. That would probably not get me a mark at IGCSE. Why not? It's subtle, but there's very wrong physics here. The radiator heats the air particles gain energy, so they spread out, becoming less dense. The mistake that I've made is, it's not the air particles that are becoming less dense. So like a particle of oxygen, say, is a proton with little electrons whizzing around the outside. That particle, or atom, or whatever you want to call it, is definitely not getting less dense or more dense. Sorry, you can't really see that, can you? But yeah, the atoms are staying the same. They're not squidging, their particles aren't getting closer together or further apart. It's the air that's getting less dense. The air is less dense. Not the individual particles of air, which is what I've made it sound like there. Oops. And the cold air is denser. So I've put cold air is pushed out of the way, or I would probably just write cold denser air is pushed out of the way and sinks, which would be a good answer at GCSE. Kitchen is very pleased that you've got those in the right order. How many examples of convection can you see below? Name and explain. What have we got? Well, we've been learning about clouds, like in all ages, if you're watching live. So they are just warm water particles which have risen and then cooled. So clouds are formed because of convection currents. the pan is hot, so hot air will be rising here above the pan, and then cold air will be falling around it. There's also a pan over here actually. Inside Earth, I've put, is one big convection current, so that's how magma works. It gets heated up deep inside the Earth, and then it rises up potentially to the surface of Earth. There's a pan here as well actually, yeah, and that's on the hob, so that would have been a convection current because the soup on the very bottom of the pan gets hot, so it becomes less dense, so it rises up, and then cools down, so falls, and that new soup is hotter, so again. Right. Explain why the little freezers inside fridges are always at the top. Well, what have I put? The coolest air is at the top of the fridge. If the freezer's at the top, that means the coolest air is at the top of the fridge. What do we know about cold air? That cold air is denser than the other air in the fridge, and therefore it sinks. So IGCSE, I would always be using the word density. And then warmer air at the bottom will be displaced. Great word, it means knocked out of the way. So the cold air is at the top of the fridge. That's denser, so it sinks down. Warm air at the bottom, well, there's no room for it anymore because there's cold air there, so the warm air gets displaced and rises up. And that gets cooled by the freezer. So in that way, all the food in the freezer gets cooled down. If the freezer was at the bottom, you'd just end up with warm, dense air at the top, wouldn't you? That was just kind of staying still because there'd be nothing pushing it out of the way because the cold, denser air would be sat at the bottom. Right. This was... It's got a dense lesson. There's quite a lot of information in this lesson. So we'll go through the answer to the little puzzle that I gave you at the start. I tried this idea of, this is a true story. I used to run through the kitchen, just leave the door hanging open, or I'd be chatting to my friend on the doorstep and my mum would be like, stop, just shut the door, you're letting all the cold air in. This was not true because heat doesn't shift from cold to hot. It goes from hot to cold. You know this because when you held the spoon, heat shifted from your body to the spoon. Coldness didn't go from your spoon to your hand. That doesn't make any sense. Your hand feels cold because it's losing heat energy. It doesn't feel cold because like coldness is going into it. Well, coldness isn't even a thing, is it? Coldness is just like a lack of heat. So the same happens with liquids and gases, fluids. When I open the door, it's the hot air that escapes. It's not the cold air that rushes in. I tried to show this yesterday by putting these spice jars on their side, hoping that we would see the warm rush into the cold. It didn't work, but I'm going to do it again anyway, just for fairness, because the others got to see me making a right mess. Here we go, you ready? Oh no, what's happened is because the cold water is very dense, the cold air has seeped also into the warm one, and they just end up kind of balanced out like that. Still cool, just not teaching the thing that I want to teach you. Put that back. Whew. There we go. Right, I said, if you printed off the sheet for my Facebook group, you've got a little page of GCSE questions. We're actually going to do something new and mark those next week because I feel like you've already had enough. I will just ask you a couple of like multiple choice questions to finish the lesson. So if you've printed off this sheet for my Facebook group, we'll mark it next week. If you haven't printed off this sheet for my Facebook group, well, you can take a screenshot now if you're fast. Or this is obviously staying on YouTube now forever. So you can always come back and look at it and answer the questions for next week anytime you like. In the next week, all right? So we're not going to do these questions, we'll mark them next week, but I thought just a couple of multiple choice to see if you've picked up on some of the things that I mentioned very quickly. What is it about the electrons in a metal that makes metal such a good conductor? What is it about the electrons in a metal that makes, metal such a good conductor? Is it A, they're very small, B, they're free to move about, or C, they have a lot of energy? It's the electrons in a metal that make the metal a particularly good conductor of heat and of electricity. And it's because, B, they are free to move around. They're literally called free electrons. When I used to be teaching in a school, you would get a mark for saying free electrons, whereas you wouldn't get a mark for just saying electrons. Which one of these words describes materials that aren't good conductors? What word describes materials that are not good conductors? Is it insulators, insulation, or invection? Which word describes materials that are not good conductors? Your air, your polystyrene, your rubber, your... Anyway, It's insulators. Insulation is something that you might like put on something to stop heat passing through it, but the name of the material is, we call them insulators. And finally, what gets less dense when air heats up? What gets less dense when air heats up? Is it A, the air, B, the molecules, or C, the atoms? The answer is, it's the air. It's the air that gets less dense. The particles spread out, and so the air overall is less dense. But the molecules and the atoms, whatever they are, they just stay the same. Right. Okay. Good. Thank you so much for joining me. So we're doing radiation next week, which is how, spoiler, heat shifts from the sun to us. You need to bring a bit of like tin foil. So if you eat any chocolate that is wrapped in, or anything that is wrapped in foil this week, save the foil and you can use it for the activity that we're doing next week. I'll say this just because I have to say it so that everybody knows there's no Lego story time next week. So if you normally come to my Lego Storytime lessons, apologies, I'm at the Institute of Physics' Science Communication Conference, which is just a lot of words to do with what I do, so I felt like I had to go. But the IGCSE lesson is still on, although actually I think it's at a different time. What day is it? It's Wednesday. No, I think you're good. Oh. Yeah, I think you're fine. Sorry, I can't remember. That's such a useful announcement. Check my Facebook page and my YouTube channel just to make sure that all the times are the same next week, but I think they are. Sorry. That was just wildly confusing than me not saying, more confusing than me not saying anything. Okay, I'm going to go over to my Facebook group and see if anyone is around to say hello to. Just looking at my... Oh, here we go. It's on the 15th at 2:30. I think that is just the Wednesday, isn't it? Yeah, it's fine. There's no change for you. Apologies. I'm going to go to my Facebook page and see if anyone has said hello to me. If you would like to support me, then you can. I've had loads of new supporters today. I'm so chuffed. It really makes my day. So not everyone can support me. That is totally fine. You can access the printouts and the lessons for free forever. Everybody can. But the people who can support me, if they do support me, that is what literally makes this my job. And I very much appreciate it. I don't think anyone's left me a comment. Well, that makes this easier. So yeah, if you want to pay me £5 a month for the fact that I am teaching IGCSE physics for free and doing the printouts for free, and they take me ages, then you can send me £5 a month, go to my BAT section on YouTube, and I'll send you, if you send me £5 a month, I'll send you my favourite past Theatre of Science magazine. It doesn't really matter how old you are, because I didn't know anything about what's in Theatre of Science magazine until I started writing it. So it's got a beautiful comic that my husband illustrated for me about how the discovery of penicillin and how it helps people is not all down to one person. It's got a free biodegradable plastic bag so that you can grow your own mould and then compost it afterwards. I'm very proud of Theatre of Science magazine. And if you sign up with £6 a month, I'll send you the latest one as well, which is about weeds. Hoping that you start to not take for granted all these gorgeous little plants that are peeping out from among the paving stones that people just tend to splutter weed killer on, which is not nice. Right. Right, that's it. No one has said hello on my Facebook page, so I can just go and be free. So I will. So thank you for coming. And yeah, I will see you all. Yeah, still good. Okay, right. See you soon, you lot. Bye.